Hey class, Mr. Houston here. Back to talk to you again about some more circles. Today we are focusing solely on a certain part of the circle, and that certain part of the circle happens to be known as the chord. We are going to be looking at what properties are involved with chords and what we can do to use them mathematically to solve some problems. So just to take a look at some examples here, some information. When you have a semicircle is just half a circle. You have the diameter, which again, remember, is a chord, and then remember that it cuts the circle exactly in half. So you have neither a major arc nor a minor arc. You simply just have the diameter and your semicircle. When you have just a chord, so not a diameter, the smaller part of the chord, or a smaller part of the circle that's created with the chord, is the minor arc. The larger part is the major arc. Okay? Alright, so Theorem 10.3 states that in the same circle, or congruent circles, meaning you either have a circle with one marked or two circles with the same one marked, two minor arcs are congruent if and only if, oh my, going back here to if and only if statements, their corresponding chords are congruent. So what that is stating here, what they are telling us, is that the minor arcs, so this part and this part, are congruent if and only if this chord is congruent with this chord, which, as we can see here, they have the lines marked. So that means these two chords are congruent, which then means the arcs are congruent. Okay? So we're going to put that into practice here. In the diagram below, you have similar circles, P and Q. They are telling us that FG is congruent to JK. They are telling us that measure of arc JK is 80 degrees. So let's mark that. JK, oh, they already marked it for us, is 80 degrees. Find the measure of arc FG. So it's already stated up here that these two are the same. So if they are congruent, then their measures are also congruent. So the measure of arc FG must also be 80 degrees. Remember, again, we're talking about minor arcs. And if you remember from lesson 2, minor arcs are anything that is less than 180 degrees. So I'm telling you that so you don't get confused thinking that we have to figure out this part out here. We're just talking between those 2 points, the smaller part of that circle. All right, go ahead and flip your notes over. A couple more theorems here to talk about. Okay. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So basically, if we have a chord, okay, we have this chord here, and then if we have another chord that cuts it right down the middle, so that it is a perpendicular bisector, I guess I shouldn't say right down the middle, but cuts it so that it's a perpendicular bisector, then that this one has to be a diameter. So this one's a diameter. And the reason that has to be is because in order to cut that in half, you'd have to go right through the middle of it, which would take you right through the middle of the circle. So that's Theorem 10.4. Theorem 10.5 is basically the converse of that, in that if a diameter, so I'm going to try and do this all at the same time, if a diameter right there is perpendicular to a chord, so we notice here that it's perpendicular to this chord here, it's got the 90-degree mark, then the diameter bisects the chord. So just remember a couple keywords here. First off, perpendicular bisector means it intersects at a 90-degree angle. Remember, bisects means to cut into 2 equal parts. Okay? So if we have a diameter that's perpendicular to a chord, then each half of that chord they're equal to each other. So let's put it into practice here. Nothing too crazy here, but it says use the diagram of circle E to find the length of AC. So they would like you to find this entire length from A to C when we're given that A to F is 7. So we're just going to apply what we know. We know that AF equals 7. We are going to need FC, so that way we can get AC. Again, perpendicular bisector created right here means it bisects this chord. So if AF is 7, that means FC is 7, which means AC is going to be 7 plus 7, which is equal to 14. Well, 14, not 17. Try that again. All right. Okay. Last theorem here, theorem 10.6. If you've noticed, we've talked a lot of theorems, so I encourage you, make sure you understand what the theorems are saying. Don't just breeze over it. Make sure we know what we're talking about. So in the same circle or congruent circles, okay, two chords are congruent if and only if they are equidistant from the center. So two chords, they are congruent if they are the same distance away from the center. Not a whole lot to say there other than it's this key right here. It's if and only if. If these distances right here are not the same, so if there's not a mark there or if they're not telling you that they're the same, then these cannot be congruent. So just keep that in mind. Using a theorem 10.6 for example number 3 in the diagram of circle C, QR is equal to ST. So we have QR, whoops, try a marker here. You have QR, you have ST. They are saying they are equal. And so just to reiterate, if they are equal, then they are equidistant from the center. Okay, equidistance meaning the same distance. So basically what that boils down to is that this segment is congruent to this segment. So we would just set that equal. 5x minus 9 equal to 2x. Solve for x. Subtract 5x on both sides. Get negative 9 equal to negative 3x. Divide by negative 3. You get x equal to positive 3. Now, we aren't done there. They want us to find CU. So CU is 2x. So we just simply would plug in 3 for 2. So CU in this case would equal 6. Okay. So a lot of information about chords. Hopefully it makes sense. Nothing too terribly difficult about it here. If you do have questions, I encourage you to bring them with you to class, and we will see you then.